All right. Hello, everyone. Yep, my name is Joe Cauteruccio. Don't worry about trying to pronounce my last name independently. It's pretty hard, long in Italian. This is work that I did with a colleague of mine, Andrew West, who is mysteriously MIA this morning, so I'm on my own. Fair warning, there is a fair bit of math in this presentation. If you don't like that, just pay attention to the soothing sound of my voice. Okay. So everyone here works in machine learning, data analysis, anything like that, you have a problem. And I guarantee you've encountered this problem before. You have two data sets, you really hope that they match, and you find out at the end that there actually is really not a lot of matching between them, right? It could be some bit of customer logs and some interaction records. They have different keys. You can't get matching keys from your data engineers, from your data provider, whatever. And someone gives you an independent key that they say, hey, we can tie these two sources together. Just give me some independent information about what these records are. And you find out at the end of the day that actually there's only like 1% overlap. But you believe that really there's like 50% overlap between these two sources. What do? Go home. Yeah, we'll just forget about it. Don't worry about it. Or we can try and solve the problem. So this is the sort of setup for this issue. We have two sources of data. Say we have a source and we have a target. And we have some small set of records that are in correspondence between these two sources. Okay? An example of this could be images. We have one data set that has clean images of faces in different orientations. We have another data set that has sort of noisy versions of those same images, and we're told that some set overlap. How can I potentially, given an image that's clean, return the noisy one, or vice versa? Thoughts? Oh yeah, feel free to interrupt me, speak up. I like to have interactive presentations. So, well, I could train a model on the overlap, but if the overlap is very small, it will be overtrained, right? We'll be overfitted to those little bits of records in the overlap. I need some way to encode the global structure of all the data in the source and the target, okay? All right. If the data comes from the same domain, say, images, rotated images, that's a homogeneous problem. If it comes from different domains, say images in RGB space versus images in grayscale, or images and text, we'll call that a heterogeneous problem. Most of the problems that we encounter fall into the heterogeneous category. And although I can't give you exact details, most of the time we're not dealing with images, it's like customer data. So the goal is we want to learn some sort of projection, some sort of map, so that we can tie the two sources together. We're going to utilize the information contained in the overlap to do this, as well as the global information of each source independently. And the result will be a flexible cross-domain representation that will allow us to tie these records, all right? So this is basically a way to increase our match rates, right? I want my inner join to produce more records, okay? All right, so let's set this up with some pretty colors. So we have a source and target domain, as I mentioned. There's no guarantees that they're in the same dimension. Let's say the source is in RA and the target's in RB, and they have some number of observations in each, N and M, okay? So I just mocked up some data here. We have two spheres. One will be the source, the other one's the target. I just rotated the target. So this is a bit of a trivial example because I have the rotation matrix, so I could just realign it. But let's pretend that I don't, okay? All right. We're also told that we have some set of records in correspondence, as I mentioned. So let's just say, for argument's sake, that I highlight the first 500 records and I say, okay, source, target, you guys are aware that you have some buddies, right? They're these black dots. Okay? As far as the rest of the points are concerned, they don't know that they have a pairing in the other domain. Okay? Okay. So the first thing that I want to do is I want to find some way to represent all of the information in the source and the target domain independently of one another. Right? An example could be, maybe I do PCA on the source, PCA on the target, and then do a model that ties the principal component projections instead of the original data, right? Turns out that really works absolutely horribly. But, it's an interesting idea. So along those lines, let's find a latent representation of the source and the target that effectively encodes the local structure and information of that data, right? If I'm doing PCA, that's something like correlation, yeah? If I'm doing, maybe correlation isn't the best measure, why might PCA not be a good idea? It's linear, right? We need correlations. So there may be some nonlinear structure in the data that I want to capture, something very rich, way more informative. Does that make sense? Okay, so let's say I take my spheres, and for one of them, I just remove a dimension. I collapse it. Let's say that's the one on the right. Is that a good transformation or a bad transformation? I've effectively encoded the local structure of the data in such a way that the relationships are maintained. Well, along the edge of the space, what do we think? It's not bad, right? Points along the edge of the sphere that were close are still close to my projected dimension, right? What about points on the top and bottom of the sphere? Were they far away from each other in the original space? What about now? They're directly on top of each other. The distance between them is 0, right? And this has to do with that loss function that I have highlighted up there. So let's say we have a loss for the source and the target. And what we're going to do is we're just going to measure the distance between points in the hidden dimension, right? Say Euclidean distance. If they were close in the original domain, right? If they were related, okay? We'll have some function, some matrix that returns a value that's big, right? So if I make OS there big, then the only way the optimization routine can minimize this loss is by forcing these points to be close in the hidden dimension. Does that make sense? Yeah? But if they're not close, then OS can be some very, very small value. It could be 0, right? So I really want to maintain that relationship from the original space. Okay? So what about the second one? It looks much different. And what I want you to focus on is the density of points around the edge of the transformation. Where do the points lie? A lot of them get forced to the edge of this sort of square thing, right? And the gradient, the color, oh yes. Because, okay, so if we learn some sort of model that ties just with the correspondence, that may, especially on the target side, may represent like a very small portion of the actual data itself. So you could have a situation where it's, say, in the images, I give you faces, but there's also, say, like teapots in an orientation, and you might overfit to faces, and then you're not really representing the target information as effectively as you can. Mm-hmm. If you try to learn about basically a matrix factorization style model, then it will effectively induce low-rank representations. Yeah. Yes, that's certainly true. I mean, here I'm actually really treating this as more of an unsupervised problem. So we're going to learn a joint embedding between the source and the target domain. But you're right. So one way that you can think about this being used is like in transfer learning. If we want to find a good transfer mechanism, you could use something like this manifold alignment. But if you do have a classification problem explicitly, there are better ways to learn this embedding so that you actually improve the classification task rather than the embedding task. So that's a good question. Thank you. Any other questions? Nope. Okay. So we have this other transformation, and it's actually maintained the local structure a lot better, right? The points have all been forced to the edge, and the gradient's actually maintained. So the blue points and the green points are sort of close to each other. The red points are still close to each other, and they're equally far as they were if we just traverse, across the shape, right? There's one interesting thing here, though. Can anyone guess if I gave you that what the original manifold looked like? I couldn't. I don't know. I'd say it's like it's a cube. Like I'd be completely wrong. We've maintained local structure, but the global structure has sort of been lost. So that's something to keep in mind. Okay. So I mentioned this core. Oh, yes. Yes, but it turns out that doesn't really matter so much. Well, no. So I mean, the shape of the embedding here, particularly this one, when I get to it later, it doesn't matter because it has a matrix factorization solution, like a decomposition solution, so we don't have to worry about the convexity of the space to do some sort of like gradient-based method for solving it. Yeah. Although it could cause issues if you do try and use something like that. A bunch of what's that? Yes. 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 It may be. It may be. So one of the things that we're actually trying to work on is finding some sort of guarantees on the dimensionality of the input data. Like, at what dimension does this become no longer, or like, is it, if it's a small enough dimension, is this useful or not useful? And most of our data falls in this sort of really annoying spot where some people might consider it high dimensional. Most people in the room who asked that question probably wouldn't. So we sort of have a issue there. No, this is not a random projection. Yes. Yep. Mm-hmm. Any other questions? Okay. I will go a little faster. So we want to preserve the correspondence between these points, right? So whatever projection we pick, this is not enough, okay? I need something that does not only preserves the local structure of each source independently, but preserves the correspondence structure between the two sources that I've been given, okay? So as you can see here on the right, I have some sort of map that's projected, say, the source and the target, the top and the bottom. They have some shape. It's interesting looking. But the correspondence between the points, the lines that I drew between the top and the bottom, are all kind of crisscrossed. You could never guess which points were actually in correspondence if I just collapse these on top of each other, right? So I need to learn this projection so that that is also maintained. Basically, so that the lines are straight. If I force these on top of each other, the points that were in correspondence in the original space, the points that matched in the original space have distance of essentially 0 or as small as possible, right? Then the logical conclusion is, if there are 2 points that weren't in correspondence in the original space, but they're on top of each other in this space, can I guess that maybe those are also in correspondence? I predict that they're in correspondence. Yes. And that's essentially the goal. Okay. So our total loss function takes both of these aspects into account. Okay. We measure the source-specific structure that we've maintained. We measure the global correspondence, and we just add it up, right? So this is what we're going to try and minimize. Okay? Yes, sir. There is an assumption here that you believe that there is a low-dimensional joint representation between these sources, right? So you have to sort of buy the fact that these two sources exist and I can map them to a common low-dimensional space. It may not make sense to do that, but in most cases it can. Yeah. Okay, maybe we should, yeah, because I don't want to go too long. We'll talk more after, okay? All right. So this is our total loss function, okay? We have the source and target loss that I highlighted earlier. We have the correspondence loss, and we have a mixing parameter alpha to balance. Maybe it's more important for me to maintain the local structure versus the correspondence structure, or vice versa, okay? All right, and I expanded there just for, I guess that's not really fun, but I expanded it for you. All right, so let me give you a concrete example, because I showed you a lot of math, and a lot of you were giving me strange looks. So the concrete example is, let's say I have pictures of the Earth, right, in some rotation. I have pictures of a creepy-looking statue in some rotation, and I have pictures of a face in some rotation. The goal would be, given a picture of the Earth, return its corresponding partner in the statues or in the face, right? If I have some set of overlap, I can use this manifold alignment technique to learn a projection that will tie the pictures of the Earth to the two other spaces. If I give you a picture of the Earth that isn't in the correspondence set, I can just look in the mapped dimension for its closest buddy in the statues and in the faces and return that observation to you, okay? The key there is that I can't reconstruct the original picture from the information in the low dimensional representation, but I could say get its index out of a matrix, right? So I can return to the index of the original observation, but I can't reconstruct it, okay? All right. So how do we do this? Someone asked a question about the convexity of the space, and I said there's going to be some sort of matrix stuff happening. This is where the matrix stuff kind of happens. So a simple way to do something like this in a linear way would be using EM-PCA. So when we take PCA, like I was saying earlier, we'll just do the eigen decomposition of the correlation matrix, right? Let's look for the directions of maximum variability in our data, and we'll project it onto that, okay? What if there's missings there? What do we do? How about we just fill them in with some random number, right? Let's do PCA, and then at the end, see how well did we maintain the correct directions of correlation among the data that we did have populated, right? Did we do a bad job? Well, that means our numbers were bad. So let's update the numbers with a new number and keep doing that until we effectively return the right correlation for the source data, the target data, and the overlap. The numbers you get out the other end will be your projection, right? It's actually a pretty simple way to do it, and it works out actually pretty well. It takes forever to estimate, right? Forever. So we're not going to talk about that because computationally it's just not really feasible for us. But we can use another method. So we're going to use to solve this one way is Laplacian eigenmap. So Laplacian eigenmap is just the eigendecomposition of a graph Laplacian of some data. So how do we form the graph Laplacian? I have a little picture there. Let's assume we have some data, and I need to find neighbors for each point. This is going to help me maintain the local structure. So let's take a neighbor, let's take a point, and we'll find its neighbor set, say using dots, k and n, right? Let's use k and n to find the 5 closest neighbors for every observation, okay? If we find a neighbor set, let's draw edges between them. And then for each point, we'll measure the degree, and we'll form an adjacency matrix as well. So that's what we have here. We have the degree matrix. It will be diagonal. It's the number of neighbors that we've identified for each point. And we'll have the adjacency matrix where we just mark a neighbor with a 1. Okay, take the difference. That's the graph Laplacian. If we do the eigendecomposition of this, we find that it's actually a very good way of representing the embedding. Okay, so I said we'll use k and n. In practice, you want to use an epsilon sort of specification rather than picking a hard number because we want to have variability in the number of neighbors for each point. It'd be a little strange to have a uniform number of neighbors for each point. You can do it. In the literature, some people do. It's sort of odd, they'll agree with you. And you can kind of play with this. Pick the number of neighbors, look at the degree distribution. There will be a sweet spot. You have to kind of tune it. All right, so I pointed out this loss function earlier, and I said that we're going to do some matrix stuff. It has a vectorized representation. That's it above. I can point you to the paper where you derive it. It's actually pretty simple, but I won't do it here. And if we take, turns out, that vectorized representation, and we form sort of a weird-looking graph Laplacian, we have some marker matrices, I call them W, where we mark the points that are in correspondence. It'll take a little too long to go over all the details here, but if we form this sort of pseudo-Laplacian and take the eigendecomposition of it, we love just doing eigendecompositions. They're great, they're simple. We have a solution to our optimization problem. So that's one way of doing this. But we're all here to talk about deep learning in some way, right? Because it's hot, it's cool, it's fancy. I get to use all sorts of computers and GPUs. I love it. So maybe we can figure out a way to kind of represent this loss function, but in more of a deep learning context. So I said I need to maintain, I'm just gonna skip. I said I need to maintain some sort of structure. I need to learn something about the source and target data, right? How it behaves. How can I do that using deep learning, using neural networks? Well, let me take a denoising autoencoder. Essentially, this is sort of like the deep learning or the neural network version of some sort of PCA, say, right? I want to learn a low-dimensional representation of my data, right? That contains all the information from the source data. What I'll do is I'll stick my data into an autoencoder. We use denoising autoencoders, so we corrupt the data with some Gaussian noise, stochastically corrupt the data going in, right? We learn an encoding function, which changes the dimension of the data to some low-dimensional representation. And then we learn a decoding function, which blows it back out. And then we measure the loss, which is just the reconstruction loss. It's the difference between the original representation and the decoded representation. Basically, how good a job did we do of retrieving the original data, right? We'll stack a bunch of these on top of themselves, and then this will be our low-dimensional representation for the source and target data. Okay, this is like our compressed form of the information. Does that make sense? All right. The next thing I said that we have to do is keep the correspondence in mind. So to do this, we're going to just do another sort of tweaked autoencoder. We'll call it a corresponding autoencoder. And it just has a little bit of a change to the loss function. Instead of reconstruction error, we're going to look at the distance between the hidden representations for points that are in the correspondence set, mainly this guy. So the overall loss looks quite similar to the one before, but it's sort of framed in terms of reconstruction loss. Okay? We'll tune this guy using a mini batch, and we'll just pass observations through. And turns out it's actually a very easy way of learning the manifold alignment using deep learning. And to program it's actually pretty simple, because you can have things like Theano and Keras help you out. We'll talk about that in a little bit. But how does this help us? So we can do that unsupervised pre-training, which turns out to be very effective. It's also a different way of learning the source individual information. Before we were looking at local structure, actually just using a graph. Here we have the possibility of learning a much more complex representation of the data. Before, if I had new points, I need to update the graph, I need to update the matrix, and I need to redo all the eigen decompositions. That is really annoying if you're trying to do this in a business context. Here, I can just pass new observations through. I may need to retrain it at some point, but to score individual observations is much more simple. All right, so in practice, what do? If you choose to do Laplacian eigenmaps, your matrices will be very sparse. There will be a lot of zeros, right? They're graph matrices. They're going to have a lot of zeros. So just use sparse matrix formats. You can do it in SciPy. SciPy has a sparse linear algebra routines you can use to get the eigen decompositions. Actually turns out to be not so bad to estimate if your data is of a reasonable size. We're working on actually trying to do some of this in CUDA, because there's cuSparse and cuBLAS that we can maybe put some of this on a GPU. There's a really annoying problem there, though, and that's the contiguous memory requirements on the GPU. If the matrices are huge, it's really annoying, and also we can't really do the matrix decomposition in sort of a batch way, but we're messing around with that. Wish me luck. The last thing is Theano all the things, right? Has everyone seen this meme? No? Yeah? So, of course, we use Theano to train our deep networks. We're thinking of maybe migrating to Torch for production, but I can't put all the code on the slide. We're open sourcing our wrappers to do the corresponding autoencoders. If anyone wants to try that, we have our loss functions in there. But yeah, basically we're just using Theano to do the training. If you have any questions about Theano, come talk to me after. We can talk about it. We talked about it. We debated it. We sort of landed on. We're still debating it, to be frank. Yeah. So there's some issues with TensorFlow that have been pointed out with like speed a little bit, especially when compared to Torch. Also, yeah. We should talk about that. It's a long discussion. Any other questions? Actually, because this is essentially the end. I have our references and our plug slide.